Good day, ladies and gentlemen, and welcome to your CUAHSI Cyberseminars conference call. My name is Jean. I'll be your conference coordinator. At this time, all lines are in listen-only mode. We'll be taking questions off the phone lines later in the conference call. If you ever need operator assistance, please key *0. At this time, I'll turn the call over to your host, John Duncan. Over to you, sir.
Thank you very much, and welcome everyone to today's cyber seminar given by Dave Gochis of UCAR. Thanks for sticking with us throughout the semester, through the thick and thin of these things, as they've most oftentimes worked and sometimes haven't. So thanks for participating in today's rescheduling of this. If you have any problems today, you can send those to me in the chat box in the lower right-hand side of your screen. And again, if you have any feedback on this seminar series in general, the vision paper ones in particular, or just in terms of the WebEx portion of it, please send those to me via email to commanager@CUAHSI.org. The presentation that's actually on the CUAHSI website isn't completely up to date. There has been a couple of revisions. As I'm out of the office, I haven't been able to update those, but I can certainly provide you with a more up-to-date copy if you'd like, and we are having this recorded and merged to a CD, so we'll be able to provide that to you via download at some point in the near future. So I'd like to just quickly mention that we still have 2 cyber seminars that haven't been scheduled. We're getting into finals time now, into the semester crunch. So these are likely to take place in January, where there will also be some cyber seminars on hydrologic observatories and services available to those teams proposing, of which UCAR may make a presentation. So more information will be going out on this as it becomes available. But for the up-to-date calendar and links to the draft papers and presentations and discussion forums, they are on the CUAHSI website. I would like to quickly plug some CUAHSI activities at the upcoming Fall HU meeting for those of you who will be there. On Tuesday evening, there is a reception where we're going to be welcoming the new board of directors and do that over cocktails and some hors d'oeuvres. Wednesday morning, there's going to be a poster session on the hydrologic observatories. And then Thursday evening, there's going to be a town hall function on the recently funded hydrologic measurement facilities proposal. At this point, I'd like to gladly welcome today's speaker, Dave Gochis, who is a research scientist with the National Center for Atmospheric Research. He got his bachelor's from the University of Kansas, his master's from Oregon State University, and his PhD in hydrology and water resources from the University of Arizona. He's active in several professional societies, including AGU and AMS. And his research interests include modeling and diagnostic research into the physical mechanisms controlling regional climate systems and hydrologic responses across the southwestern U.S. and North America, as well as enhancement, development, and testing of surface water and energy exchanges in the community NOAA land surface model. So, Dave, I'm glad to have you back today. Thanks for sticking with us through this, and I'll turn the presentation over to you.
Great. Thanks a lot, John, and welcome, everybody. It's a real pleasure to be here providing one of these. I think my phone just beeped, but I guess I'm still on. Let me welcome everybody again, if they've missed out, to one of these CUAHSI cyber seminars. It's a real honor to be able to participate in this effort. There's been a number of many excellent presentations, and I've personally learned a lot so far from many of these seminars as they've gone on, and look forward to participating in this effort as we move forward with the development of the CUAHSI program. Let's see. There we go. I'm going to start with an image that is where we've come to in terms of meteorological and hydrological research and the interfaces thereof. This image of a thunderstorm over the Great Plains region of the central United States represents the culmination of many events and the initiation of many more events. And when we've looked at this historically on a case study basis, what we've seen is that the meteorologists tend to approach this a little bit more in the retrospective sense, looking in detail at the events that lead up to the initiation and generation of a particular precipitation event, and oftentimes really ceasing their studies once the precipitation has ended. The hydrologists, on the other hand, their work often begins only when the precipitation event begins. Much less emphasis historically has been placed on interstorm periods to particular rainfall and snowfall events and the hydrological responses thereof. But what we've begun to see here in the last several years, perhaps decade or so, and I think we'll see more and more in the future, is a continual erosion of this divide of research approaches as we need to develop a more and more continuous, temporally continuous model framework. Some of the tools we use to describe these, at least in terms of the atmospheric modeling sense, are things called land surface parameterizations, and they've been talked about briefly in some of the earlier presentations. This is one called the community land model that's given here, and we can see a variety of exchange processes occurring between the terrain surface, the vegetation canopy, and the overlying atmosphere. This on the right, on the left side here, representing some of the biogeophysical exchanges, and on the right side, some of the hydrological exchanges. But I think it's fair to say that the complexity of the real-world systems is far and away exceeding our capacity of any one of the disciplines that we use to study these, and that these approaches or these abstractions that we've had have often been ad hoc in nature, and we really require a much more comprehensive effort to move beyond this. Okay, how do we, at least in terms of NCAR, come to get involved in this process? Well, we started a little bit over a year ago when Rick Hooper visited NCAR, and we started discussing the methods for which a collaborative partnership could be developed between CUAHSI and NCAR. And things came up such as the long-term hydrological observatories, utilization of computational resources, various personal scientific networks, etc. And I think it became quickly obvious that we needed to develop a more direct dialogue, at least institutionally, between the atmospheric science community and the hydrological science community in various regards with particular individuals in the science community for quite some time, but really bringing to bear the force of some of the institutions would have some great benefit in this effort. And so what this resulted in is a voluntary effort by several people here at NCAR, as well as within the university research community, and at a few of the other national centers, such as NCEP, the National Centers for Environmental Prediction, to develop a 10-year vision for advancing coupled land-atmosphere interactions. So here's a list of some of the initial collaborators. You can see some participation across a number of the different divisions here at NCAR. I definitely would like to note the participation and contributions of Mike Eck and Ken Mitchell of the land modeling group at NCEP, vastly improving the quality and the breadth of the document that we've submitted to date. And would also say that there's a lot of university contributors who participated in a number of other ways to this effort. And like many of the other groups, we see this as an evolving effort as time goes on, and welcome any feedback towards the vision that we'll be presenting. Okay, the presentation today is going to proceed basically as follows. I'm going to give a quick background on two elements related to land-atmosphere interactions. First, I'm going to talk about the forecasting paradigm that we currently operate under, and then talk a little bit about the evolution of these land surface parameterizations as they're used in atmospheric models. Then I'll move on to the various themes of the 10-year vision, and these include some of the critical gains in understanding we'll witness over the next 10 years or so, some of the emerging platforms, observing platforms that are going to move off of the horizon into view, some of the core model development activities, and then analysis and prediction systems. Following this presentation of what we expect to occur over the next 10 years, we'll lay out a strategy as part of the vision for some ideas that we have in terms of facilitating the realization of this vision, and then, if we have time, talk a little bit about some of the community impact of the vision. Excuse me. I want to say a little bit about what this presentation is not. This is definitely not an attempt to siphon off resources away from CUAHSI. We're very sensitive to the fact that NCAR and CUAHSI are two, what would be two leading elements or program elements under NSF, and various tendencies might occur for competition between funding to arise. And I just want to say from the outset that from an NCAR point of view, we hope that this can be mutually beneficial in absolutely every regard, and we don't see the participation as any attempt to try and siphon resources away from CUAHSI. In fact, we value CUAHSI and the contributions that it will make and want to see its success in as many ways possible. This presentation and the vision statement itself is also not a holistic science review. The previous Grand Challenge documents that have been listed before have done an excellent job of laying out some of the foundations of where we've come and the state of the science. Again, what we really seek to forward here is what we expect to occur over the next 10 years, and in that discussion we're primarily limiting ourselves to water cycle physics at the unfortunate expense of discussing biospheric and geochemical systems. There is a lot of text in the document related to these, but in terms of presenting those for the presentation today, we had to make some sacrifices in lieu of the time constraints. And then the third thing is that hopefully we hope that this is not just strictly an atmospheric scientist vision. We want to forward this Earth systems modeling framework or concept. It was mentioned a few weeks ago by Jeffrey Tynes' group and is being undertaken among a variety of different institutions, both nationally and internationally. And we hope that some of the elements that we're proposing and discussing here today would contribute towards a more integrative framework as opposed to just that of a subdiscipline. Some of the desired outcomes would be, again, an understanding of the practical achievements at the interface of atmospheric and hydrological sciences. But I think what's most desired out of this presentation and the vision statement effort, at least from the NCAR end, is an improvement in the partnerships between the atmospheric sciences and the hydrological communities. Again, we see CUAHSI as a very organic movement to forward hydrological research, and we would like to help facilitate and participate that in any beneficial way possible. And in doing so, we hope to foster various avenues of collaboration, such as participation in visiting scientist programs, leveraging on community facilities, and the improved infusion of hydrological science into atmospheric prediction systems and vice versa. And hopefully these things will come about via these 10-year vision statements. Okay, now I'd like to shift gears a little bit and talk about where we're at in terms of, I guess, state-of-the-art forecasting techniques. And this is a diagram that's been modified from Jagadish Shukla, I forget the exact reference at this time, from George Mason University, excuse me. And basically what this presents is a dynamical downscaling framework for environmental prediction. Essentially what one does in the scope of making dynamical forecasts is begin with a very large core scale, global scale, land, ocean, atmospheric data assimilation states for various prediction systems. In this sense, a very core scale, global, coupled ocean atmospheric modeling system. One of the main products of this is a forecast on the seasonal to interannual scale of sea surface temperatures. This can also be done via statistical method, as shown here in the dotted line, but we're going to focus today on some of the dynamical methods outlined in the solid lines. These core scale long-term outputs are often used to provide additional conditions for high-resolution atmospheric model forecasts, and these are coupled land atmosphere model forecasts, but often don't have an ocean component associated with them. These types of models are often run at a much shorter time scale, on the scale of a week or two to a month, and therefore can be run at a much higher resolution. We're indicating here on the order of 50 to 200 kilometers. Nesting down is to run a regional scale, even higher resolution forecast model over a particular domain of interest. Oftentimes, at least in the state-of-the-art sense, the U.S. and Europe and many of the other leading meteorological agencies have developed both regional land and atmospheric data assimilation systems to facilitate the initialization of these models, and then the boundary conditions come from the coarser resolution global forecasts. Now these forecasts are run, again, over a limited domain such as the continental U.S. or North America, and basically provide the detailed weather forecasts that we know today. And these weather forecasts then often form the basis for local regional applications forecasting models, be them hydrology, rainfall runoff models, agricultural growth models, environmental quality forecast, transportation, power, etc. And then that information, therefore, forms the basis for various decision support systems. Now, we don't intend to say that this is the only method of doing forecasting, but this definitely seems to be the current paradigm that many of the national agencies and institutes are operating under right now, and would just like to use this as a background for some of the detailed stuff I'm going to talk about a little bit later. Now, one of the critical components, at least with the most relevance to this group, of that modeling framework is the land surface parameterization, or LSP, as they are employed in atmospheric models. And what we've attempted to construct here is an illustrative genealogy of these models as they've evolved from their simpler beginnings towards their later states in their lifetime. Clearly, this is meant to be illustrative more than definitive, and shows many of the key evolutions involved in various land surface parameterizations. It's also worth noting that there have been and will likely continue to be alternate pathways to this evolution with occasional generation skipping, as we see designated by some of these arrows that skip generations. It's also worth noting that many of the components are intricately linked, and progress along any one discipline may be dependent among several of the other disciplines. So just stepping through these rather quickly, we've begun with the first generation bucket models, or more or less mass balance models, and these evolved into the second generation models, which employed a very basic treatment of plant canopies and resistance formulations for regulating transfers of energy and moisture between the atmosphere. These in turn evolved into more sophisticated models which began to couple photosynthetic processes with energy and water exchanges, and gradually improved the sophistication or complexity in the treatment of plant canopies. Fourth generation models began to look at a more complete carbon cycle, looking at things like carbon exchanges within the soil, overlying litter layers, and plant canopies, and how, in a much more detailed sense, water and energy exchanges are regulated by the carbon cycle. Again, increasingly more sophisticated treatment of the plant canopy, including the development of dynamically evolving vegetation models. These are models that basically allow leaf characteristics to change over the courses of a season or several events, disturbance events if necessary. And I think this is essentially where we are in this day and age, although there's a lot of research that is being done to move onward into the so-called fifth generation region of these eco-hydrological models, which have more complete treatment of the entire water cycle, and by that I mean more sophisticated treatment of soil hydrology in terms of snow processes, and also in terms of biogeochemical cycling in the model. And so as we move forward, this is definitely the framework that we tend to be leveraging on, and I'm going to refer back to these fifth generation models as time goes on throughout this presentation. Another aspect of these fifth generation models that is beginning to be quite evident is the implementation of human management and alteration of various components of the land surface, in particular the water cycle, which can account for things such as groundwater pumping, interbasin transfers, large-scale irrigation projects, and the like. And these have become an increasingly more important aspect of environmental prediction. Okay, so that essentially wraps up the background from where we're going to be talking about the vision from here on out. Our goal, of course, is to make the measured improvements in weather predictions and forecasts. I'd say we need, but we're well poised to make critical gains in our understanding in improving many of these forecasting techniques, and we'll talk a little bit about what those are. But it's worth mentioning some of the obstacles as well. First and foremost is this multi-scale complexity issue. It's been elaborated on by many of the other speakers, so I'm not going to spend any time really talking about it, but I don't want to diminish the problems associated with this, and we feel it's an important task and is in many ways limiting our ability to improve forecasts. But some of the other aspects I did want to mention are the erosion of many of the long-term observation networks. I was very surprised a couple of weeks ago to be at a conference in Madison, Wisconsin, and somebody gave a figure for the loss or the attrition of USGS stream gauges over the last 10 to 15 years, and was really shocked at how much data we have lost compared to some earlier points in our observing networks. Another critical feature of adding complexity to environmental predictions is those issues related to global and regional climate change and potential acceleration of the water cycle. Coupled with that, rapid land use changes, urbanization, and large-scale manipulations of hydrologic systems, we're faced with some fairly daunting tasks moving forward. So hopefully that's most of the bad news at this time, and I'm going to try and move into more of the good news, which is where I think we're going to be headed over the next 10 years. And this was a list that was compiled by many of the different participants in this area from a wide variety of disciplines, from micrometeorology to land surface interactions to observing techniques, instrumentation, etc. So we've broken the vision into 3 different themes, and they are the utilization of emerging observation platforms, and I'll give a brief description of some of these platforms that we feel will add great value to coupled hydrometeorological research. I'm going to spend a little bit more time talking about core model and theory development, and then try and synthesize those 2 discussions by relating them to their improvement in analysis and prediction systems. So theme 1 is the utilization of emerging observation platforms. Now, Vitek Krajewski's group, I think, gave a very excellent summary from a remote sensing point of view about what some of these emerging platforms are, and I would defer to his talk completely in a more detailed sense of many of the different frameworks that need to be exploited moving into the future. What we would also endorse is their proposition for this remote sensing observation as a field validation effort for many of these systems. But I'm going to focus here shortly on a few other systems that weren't discussed so explicitly in that presentation. One of those being the advances in weather radar, a brief mention of spaceborne platforms, and then some of the instruments used to probe the planetary boundary layers. So I think one of the things that will have the most significant impact on hydrological operations and research over the next 10 years or so are some of the proposed and actually planned enhancements of the NEXRAD weather radar, the U.S. Doppler radar network. This is primarily consists of upgrading the current network to a dual polarimetric capability. Now, what this polarimetric capability gives you is retrievals at dual polarities and offers, with some processing and of retrieving information from cloud and cloud reflectivity signatures. Information on cloud and raindrop size distributions, microphysical characterizations, and improved detection of ice and liquid phase precipitates within the clouds are just some of those. Right here in this diagram, we've shown a plot of several of the different new products that are going to be coming out. Basically, today we're looking at retrieving standard reflectivity and then relating that via some empirical relationships to rain rates. With the dual polarimetric capabilities, we'll have a wealth of more information available. This diagram right here, which is under the title of this log NT per meter cubed, is actually a count of hydrometeors per cubic meter. So getting a bit of a count of the hydrometeors that are in a particular scan volume. And then associated with that, if most hydrologists have gone through the exercise of doing a particle size analysis and coming up with an effective diameter of particle size for a given constituent or a given sample volume. That's essentially what we're plotting here. This D0 as a function of millimeter gives you an estimate of the size of the hydrometeors within a particular scanning volume as well. And combined, these give you the so-called drop size distribution. This, in turn, can be related to the density of water mass per unit volume in the atmosphere, which has a much more direct relationship to actual rain rates than do just some of the basic reflectivity measurements as we're dealing with now. Now, hydrologically, the benefits for these enhancements I don't think are at all trivial. Essentially, this will result in improved quantitative precipitation estimates in complex terrain and in mixed phase precipitation situations, which can, in some instances, result in a 30 to 40% bias reduction in precipitation estimates. Improvements to the computer hardware that runs the radars will result in higher spatial resolution scans and faster scans, which will enable a better resolution of temporal and spatial intensity structures, which of course are critical for runoff partitioning. The improved microphysical characterization will also have a direct impact on improving the depiction of freezing levels, which are important in the transient snow zone. And I'm going to refer here to the figure that's plotted over here. This top figure is a cross-section of radar reflectivity with height, and this bottom cross-section is the same cross-section, but where the hydrometeor classification has been done. And it's quite evident to see in this that from a remotely sensed point of view, we're getting a very clear depiction of where the freezing level is, or the transition from ice phase precipitates to liquid phase precipitates are, which can be very important for studies such as rain on snow events and freezing levels in the atmosphere, something which is not an exceptionally well confidently estimated parameter at this time. The various classes of microphysical elements can allow for improved estimates of snow crystal density, and the improved drop size distribution, as I mentioned earlier, will allow for improved quantification of raindrop momentum, which of course is very important for a number of different erosion studies. However, all of this needs to be rigorously validated once it's put in place in a variety of different regions. And I think, again, this remote sensing observatory, as VTech's group proposed, would go a long way in satisfying or meeting this need. Briefly now about some of the emerging spaceborne platforms critical for hydrometeorological research. One of these being the NASA GPM mission, the Global Precipitation Measurement Mission, which will be providing global coverage of radar estimated precipitation from a spaceborne radar with 3-hourly global coverage. Now that's obviously this product can be a bit coarse in terms of a lot of the processes that we're used to dealing with in the hydrological sciences, but providing this global capability is obviously very important in regulating the large-scale hydroclimatic regime. Another element is this NASA Hydros and the European component, the SMOS mission, which is basically dedicated towards developing a remotely sensed capability of near-surface soil moisture and near-surface freeze-thaw states. The image that's shown here on the right is some products from this summer's North American monsoon experiment that was done during August of this summer. And what we're seeing is the response of the near-surface soil moisture states to monsoon rainfall throughout a variety of different locations in northwestern Mexico and Arizona. And then just adding on to this, a number of different platforms which will have a much improved resolution to characterize land surface, land use, land cover types, land surface conditions, and things of that nature. All of these obviously are going to be contributing to our ability to characterize the terrain and its potential influence on hydrological and atmospheric responses. Okay, the atmospheric boundary layer. I think one of the things that's really exciting is this improved distribution of in-situ flux networks that we're seeing being conducted under Ameriflux and FluxNet and various other ones that I'm sure people in this group are participating in. Really offering us now much more in the way of validation points for many of the atmospheric models that we've been running and over the near history, I guess, and really providing us some constraints on what these models have been giving us in a variety of different ecotypes. And hopefully over the next 10 years, this effort will continue, and we'll have longer-term data sets, of course, to work with. There's additional techniques being used to probe the planetary boundary layer. One of those is a technique to mine additional data from weather radar. This is the so-called enhanced Doppler beam refraction method. And what this is allowing us to see is with much greater detail, and this is being done from the existing Doppler network, allowing a much clearer picture of planetary boundary layer structures, things such as convergence and circulation features, which have often been missed, but can be critically important for the initialization of various weather forecasts and precipitation initiation studies. Perhaps even more importantly, and I think Vitek's group, he mentioned this in his talk, was the advances that are being made with LIDAR. In particular, we're talking here about the water vapor differential absorption LIDAR, or water vapor dial, as it's called, really giving us an unprecedented capability to look at TBL humidity structures on the order of about 100-meter resolution. And one of the real benefits of this comes from when we combine this information with that of the Doppler radar and being able to look at very detailed near-surface moisture advection patterns. Of course, this being very critical for precipitation initiation studies as well as microclimate processes. Okay, that's the sampling, at least in terms of what I can cover here, of the emergency platforms, or emerging platforms that we could hope to see and will hopefully expect some benefit from over the next 10 years. And we'll talk a little bit now about some of the core model developments that will be witnessed. And essentially, this is more of an articulation of this evolution towards fifth-generation LSPs in weather and climate models. I think it's quite clear that computational capacity continues to permit a marked improvement in spatial resolution and complexity of weather and climate scale models. And I've listed here some of the state-of-the-art length scales which have been applied to existing operational and research mode models. Weather models tend to be on the 10-kilometer or so and below scales, and climate models in the several tens of scales to a couple hundred scales. What this means, especially in the case of these weather models, is that many of the crude formulations that we've been using and have rightfully been loathed by many hydrologists throughout the past are now becoming very inadequate for their intended purposes these days. And I'll talk a little bit more about that in a bit. And also, another important aspect is that the dynamic Earth-human system, or the human influence on Earth systems, is demanding a more complex, spatially explicit formulation of these land surface parameterizations, and we need to be able to acknowledge many of those impacts in environmental processes. Okay, so now I'm going to go through somewhat of a laundry list of what some of these improvements might be. I'm going to start here with improvements in soil hydrology. This is obviously not a new issue from a research standpoint, but again, just reiterating that as we move forward towards these fifth-generation models, we need to move into more sophisticated treatment. And one of these would be the transition, at least in higher resolution models, from the one-dimensional vertical formulations to three-dimensional spatially interactive formulations. And the graphic I have shown here is just an illustration of some work we've been doing with the NOAA land surface model by implementing subgrid routing of overland flow and subsurface flow. Basic elements that have been worked and developed with in hydrological models in the past, but now employing them in an atmospheric modeling framework and using that improved process knowledges for studying smaller scale hydrometeorological feedback. We also need to advance the sophistication and the representation of soils, particularly in these atmospheric models. Soils are often characterized as having a uniform depth over very large areas and having a uniform soil type with depth. Any hydrologist knows that this is we need to go a long ways in improving our methods to deal with this, either in some sort of subgrid statistical methodology or in a more spatially explicit treatment as well. Again, along these lines, we need to improve our treatment of plant root functions and their influence on sequestering moisture. And I think some recent papers by some folks at MIT have done a very good job at looking at some of the competitive structures of plant root function in varying communities and some of the influences they have on the spatial heterogeneity of soil moisture. And we need to try and incorporate some of these methods into these land surface parameterizations. And again, these are all areas where hydrologists are bound to make significant contributions, and I've listed a few of the other talks that have touched on these elements as well. Another area, obviously, is snowpack. It's the principal forcing mechanism of the land surface on interseason variability. Roger Bales talked extensively about this in his talk a couple weeks ago, and so I'm not going to belabor it too much. I couldn't do much more justice than he did to it by any means. But suffice to say, we definitely agree with many of the points that his group has put forward in terms of needing to improve subgrid representations of patchy snow cover, and snow water equivalent, especially in regions of complex terrain. I think we'll begin to see this as time moves forward. We need better representations of the structural features of snowpacks to improve their energy budgets and the ablation of snowpacks, and again, to utilize the available and emerging remote sensing observations to improve not only the characterization and extent of snowpacks in a two-dimensional sense, but also using the aforementioned information that will be coming from Doppler radar to look at precipitate snowpack interactions, whether one has a snow-on-snow event or a rain-on-snow event. Obviously has a big impact on the energy exchanges between the snowpack and the atmosphere and in the hydrological responses. And then the final area here is improvement of land cover heterogeneity and complexity. With regard to land surface parameterizations, I think it's safe to say that, especially at the finer scales, we need to move beyond some of the more simple statistical techniques that we have been using to represent land surface heterogeneity as we begin to acknowledge and incorporate methodologies that deal with the organizational states of land surface conditions. And I think this is particularly true in complex terrain regions where we have large gradients in topography and soils and vegetation communities and microclimates as well. Often the juxtaposition of these features is very important in driving the local hydrometeorology. We need to relate these states and their respective scales to their influences on atmospheric phenomena. Particular research questions of interest in this regard are precipitation initiation and persistence on kind of the weather time scale, drought on some of the longer time scales, and there's various national and international programs looking into this, things such as the ALMA and the GLASS and the GLACE programs, providing a framework to study some of these science questions in more detail. And again, trying to come up with some improved sophistication and representation of vegetation structure and dynamics. And again, as some of the other groups have mentioned, because the vegetation is often one of the critical linkages between the ecohydrological cycles and the overall global climate system. I'm going to skip over this. I was talking here a little bit about some of the improvements needed for land surface conditions and planetary boundary layer interactions. And I think VTEC's group pointed some of these out in some pretty good detail. So in the interest of time, I'm going to skip over this. But I just want to say that this is an area where it may not be as obvious that hydrologists can make contributions, but I think there is a certain need and perspectives that hydrologists bring to the table in terms of the representation of surface processes, especially things related to land cover, roughness, events or situations that are ripe for improvement and improved treatment in our modeling systems, and hopefully some work can be made in that regard. Some progress can be made. Okay, so on to theme 3 then is going to focus a little bit on synthesizing the 2 previous themes into the improvement of operational analyses and prediction systems. Now, transferring an increased observational capacity and process modeling into an improved predictive capacity is not at all trivial. One of the methods that's been kind of come of age in the last few years are these land data assimilation systems. They're being developed and operated at a number of different national institutions as a means to integrate more information into the model characterization, initiation, and constraining process. And the framework I'm going to use here is one that's being used in the current NASA and NCEP LDAS program, Land Data Assimilation Program, where we take observed meteorological forcing and use it to drive an offline LSP, either with or without constraints or optimization functions in the process of developing initial conditions for some other environmental prediction forecast run, whether it be a weather model or a predictive hydrological model with some sort of precipitation forecast. Again, this is the framework, this diagram here, taken directly from NASA, showing this process as it is implemented with regards to initializing the NCEP ADA model, which is basically the primary national weather forecast model at this point in time. This is the North American LDAS ADA program listed here. Now, what's of particular interest to hydrologists in this effort is a couple of things I'm going to point out here. One is that if one is to go through this exercise, you often see a multi-year spin-up period for the land surface model to come to equilibrium. We also see that one of the state-of-the-art systems is being run at a 1 kilometer spatial resolution, and that should set off some bells in one's head. Running a land surface model at 1 kilometer spatial resolution for a very long period of time, it's clear that more detailed hydrological processes are going to have some effects on the water cycle states than are what are currently accounted for in many of the state-of-the-art land surface models, and we need to make some improvements to account for those. So basically, we need to advance scale-appropriate land surface parameterizations to serve in this new capacity, and we also need to find methods to assimilate additional hydrologic information. Things such as soil moisture and brightness temperature are being investigated currently, but we also need to look at improved methods for assimilating near-surface humidity structures from some of the aforementioned platforms, groundwater and aquifer conditions into some of these models, as well as stream flow, as these two components obviously provide a significant influence in and around riparian areas and their functioning between land-atmosphere exchanges. I think effective assimilation of these parameters will offer additional constraints on modeled energy and water budgets, but it's clear we're going to need dedicated treatment in these fifth-generation LSPs in order to do this. Also, in terms of improving operational analysis and predictions, I think we're likely to see the continued application of this Shukla staircase downscaling framework in both coupled weather and climate predictions. One of the things that's been interesting to see over the last 10 years or so has been the communitization of many of these weather and climate models. We've seen a handful of leading models emerge and been developed with relatively open and reasonably well-documented software architectures, and oftentimes having community working groups and user support mechanisms to facilitate their use. This framework has fostered widespread evaluation and development of these models throughout the traditional communities, but also into some of the fringe communities as well. I think we're beginning to see somewhat of a similar consolidation, at least from some of the operational institutions, in terms of the particular land surface parameterizations. And there are various programs underway, such as the PILPS program, to evaluate these models as such. And as they move forward, I think we'll see more and more commonalities drawn out, those being elements from the successful models. What's the question in my mind, and maybe for discussion in this group at a future point in time, is a similar consolidation being seen in watershed models? My experience has been that there's a large diversity in watershed models, which are often developed with a lot of very locally motivated processes. And I guess a question is whether or not there's a lot of cross-fertilization from the various communities in this effort. I think this communitization of land surface parameterizations, though, is offering a really, I guess, traditional hydrologists and other Earth system scientists to participate in their development beyond what is currently being exhibited. By having these common frameworks and user support groups, that enables an independent investigator to test and verify and improve processes in some of these models, things such as snow processes, vegetation, soil hydrology, and groundwater. And we see this in a number of the different conferences and symposia at a lot of the different workshops we go to. It allows one to easily implement new and accepted methods from, in particular, watershed catchment scale models, and I hope this becomes more, I guess, a more prevalent activity as we move forward in the future, and would like to see this advanced in terms of how how we proposed our vision here. This could also allow for improved physical representation of other eco-hydrological processes, and also using some of the methods from the hydrological community to deal with prediction uncertainty. In particular, I'm referring to the use of ensemble predictions. It has been done in the hydrological community for some time, but is more only recently making its way into more traditional atmospheric science predictions. A lot of this knowledge can easily, I think, be transferred between the two communities for the benefit of the various communities. Okay, so that was essentially the vision, and now I'm going to spend a couple of slides here talking about a strategy that we would like to put forth for facilitating this vision, and essentially recognizing the importance of improving the representation of land surface physics in coupled land atmosphere systems. We're proposing a large multi-institutional collaborative effort aimed at facilitating the following elements: defining a list of common modeling frameworks and data standards for supporting cross-discipline land-atmosphere interaction research. I think this is broadly in line with CUAHSI's overall mission, but more specifically, I wanted to focus on here is our core vision element, which is to develop a community land surface parameterization testbed facility to provide computational, scientific, and logistical support for land-atmosphere interaction research. And I'll spend another slide or two going into some more detail about that. A third element is a community education and outreach component, which I think is absolutely essential to ensure the success of the proliferation of various land surface parameterizations throughout the community, and using that as a mechanism for feedback between the research and operational communities. It looks like time's getting short. I'm going to skip some of the details on element 1 here. I think it was pretty obvious as to what we're after, of trying to define a more narrow scope of common modeling and data frameworks that can be used for community research efforts. But building on that, develop a land surface parameterization testbed facility to support computational, scientific, and logistical activities in land atmosphere research. And very broadly, this facility would leverage on community architectures as they were defined under the first element through a series of, say, workshops and ongoing national and international programs. Again, the GWEX efforts in the GLASS program, data conventions under the ALMA program, things of that nature. And then foster community guidelines for particular code enhancements, but more particularly testing and diagnostic metrics for the various modeling systems. And conceptually, we see the testbed facility operating as such, where we have a diffuse array of hydrological, human, and earth systems research being conducted, and the community land surface facility parameterization harvest this information and rapidly entrain the promising research findings into the various LSPs used in operational prediction tools. This in turn would support the development and testing of the next generation of land data assimilation systems, and also provide a framework for assessing the impact of the emerging data streams and improved model formulations on diagnostic and prediction systems. Again, these prediction systems being the core element to improving the various decision support systems. Element 3, again, is the community education and outreach component, and really this is offered as a measure to ensure the success of such an effort, of such a collaborative effort. We've seen this, I think, be useful in a number of different other frameworks, and expected it would be useful in the field of land surface parameterizations as well. But basically establishing mechanisms for user support and transferability of data and models to the research community and to the operational community here. And this could take the shape of various periodic data, model tutorials, various visiting scientist programs, and I think a key element also would be the graduate student internships. Graduate students actually coming to a facility, sitting down, working with a model and with other scientists in the field, and then taking their model and expertise back to their home institutions for the benefit of their local research. Okay, so that was essentially the strategy we've laid out. Some of the linkages to programmatic elements I'm going to mention here. I'm going to skip through these again because time's getting a little short, but I do want to mention the hydrologic observatories, as this is obviously a topic of keen interest to many of the participants here. Being realistic, the scale and extent of most of the proposed observatories is rather small compared to those in typical weather and climate forecasting operations. I don't think it's reasonable to expect that some measurements over a hydrological observatory can have a pronounced, a very profound impact on the national forecasting, weather and climate forecasting efforts. But if one was to focus on that, I think that's really missing the point. I think the point is that the data from the observatories will be absolutely invaluable, and many offline studies designed to improve the LFT physics, as well as the conducting of very limited high-resolution forecasting experiments to study particular processes. And some of those could be studying the physics of orographic precipitation events, convectively driven precipitation events, and the hydrological responses thereof. And I also see the hydrological observatories providing a critical opportunity to study the human impact on local and regional hydrometeorological processes. Things, again, such as the influence of large-scale irrigation on precipitation, various impact on microclimates, rainfall runoff studies, changes due to land cover changes, and things of that nature. All things which become more important as we move into the fifth-generation modeling systems. I'm going to skip that just in the interest of time and focus here on the Hydrological Synthesis Center. I think a testbed facility could potentially serve a principal role of the Hydrological Synthesis Center by providing a mechanism to rapidly transfer hydrological research into operations. With strong links to the weather and climate communities, we can ensure that promising research is infused into both data assimilation systems and prediction systems. And I think this is one of the aims of the Hydrological Synthesis Center. A testbed facility would also foster increased collaboration between the atmospheric and hydrological research communities. And lastly, a couple of bullets on the community impact. We would definitely, I guess, foster better integration of emerging elements of hydrological research for the benefit of improved weather and climate forecast. And I think such a testbed facility for land surface parameterizations would go a long way in doing that. And also to enable an improved elucidation of terrestrial atmospheric linkages, which not only serve as kind of the coupling of the water cycle, but also as these biological and chemical pathways, again, that many of the other groups have focused on. And with that, I am going to wrap it up and thank everybody for their attendance and would gladly take any questions at this time.
Ladies and gentlemen, if you'd like to ask a question on the phone lines, key star 1.
Well, Dave, thanks a lot. I thought that was a great presentation with a very tractable approach about how to achieve that vision.
Thank you.
In addition, if you want to ask a comment or question, don't want to do it over the phone, you're welcome to do it in the chat box, and you can type it there now.
And there are no questions on the phone lines, gentlemen.
Dave, do you see the one from Penn State?
I do. It looks like Penn State is asking, what soils information would you hope to have for improving fifth-generation land atmosphere models? I feel this is a rather good question coming from Penn State as one of the major providers of soils information that are used in these modeling systems via the StatsGo database at this time. And I think there's a lot of wealth of information already in that database that is probably not fully utilized at this time, but I think there is additional information, again, as I discussed, related to soil depth characteristics and the layering, the soil structural characteristics that may actually be there but aren't really making it into some of the more state-of-the-art land surface parameterizations as they're implemented in atmospheric models. I think if one is to implement data from StatsGo into a hydrological model, they tend to enable or specify in a bit more detail some of those characteristics such as soil depth and soil structure and soil types. But at least in the NOAA land surface model, which I'm most familiar with, and also in the CLM model, you don't have any of that layering structure of soils, or at least you don't tend to have it as much. This is obviously an area that's ripe for improvement, as is looking at this in a heterogeneous sense and coming up with some ways to do this in a subgrid fashion, to statistically or I guess, explicitly aggregate these fields. I hope that answers your question. I don't have other particular information besides that, but would see more of that data making it in.
Great. And Penn State, if you want to follow up, feel free to do so. Are there any other questions in the queue? Gene?
And there are no questions from the phone line, sir.
Okay. Well, it is about the top of the hour. I've noticed that a couple people have already exited, so they probably have to get out of whatever room they're in. I guess we'll have one last chance to ask questions, and then I will also remind you and encourage you to use the discussion forum that's on the CUAHSI website if you have any questions or comments for Dave and his team after we wrap up today. So, Dave, thanks again to you and your colleagues for the effort that went into this, and thanks for bearing with us through the technical difficulties of WebEx. But it was
no problem.
So,
yeah, thanks a lot for the opportunity. We definitely appreciate it and look forward to working with you all in the future.
Definitely. Any last questions?
There are no questions, sir.
Okay. Well, thanks a lot, everyone.
Ladies and gentlemen, thank you for joining us on the call today. You may now